Hello learners. In past lectures, we learned how to find the mean, variance, and standard deviation of regular variables. In the next few lectures, we will be expanding that knowledge and learning how to find the mean, variance, and standard deviation of random variables, starting with the discrete random variables. Before we move on, what do we understand by mathematical expectation of random variables? If x is a random variable with probability mass function f of x given that x is discrete, or probability density function f of x if x is continuous, and g of x is another function of the random variable x, then the mathematical expectation of g of x can be defined by the expectation of g of x equals to summation of g of x times f of x if x is discrete, or the integration of g of x times f of x dx if x is continuous. Again, to clarify, if x is a random variable and g of x is a function of x, then the expectation of g of x is defined by summation of g of x times f of x if x is discrete, or integration of g of x times f of x dx if x is continuous. So the mathematical expectation of g of x is also known as the expected value of g of x or the mean of the distribution of g of x. This was the general definition of mathematical expectation of a random variable. Let's look at the more specific cases, starting with discrete random variables. If x is a discrete random variables, which can either take finite or infinite sequence of possible values, x1, x2, xn, and so on, with corresponding probabilities f of x1, f of x2, and so on, then we can define the mathematical expectation of the random variable x by this formula. So the mathematical expectation or the mean of the random variable can be denoted by mu, and if x is finite, it can be defined as the summation of xi times f of xi for I equals to 1 to n, or if x is infinite, then it's the summation of xi times f of xi, where I goes from 1 to infinity. To reiterate, the mean or expected value of a random variable x is defined as the summation of the product of the values of x and their corresponding probabilities. We will now look at a few examples to see how this is implemented in practice. For the first example, let x be a random variable with probability function defined as follows. So we have the values of x as 2, 4, 6, and 8, and we have their corresponding probabilities. What is the expected value of x? So, according to the formula, we can write that the expected value of x is defined as the summation of xi times f of xi. So for our given example, that would be 2 times 2 over 10 plus 4 times 1 over 10 and so on. Again, we have 2 times 2 over 10 plus 4 times 1 over 10 plus 6 times 4 over 10 plus 8 times 3 over 10. That is equals to 5.6. So, the expected value of the random variable x is equals to 5.6. Or, the mean of the random variable x is equals to 5.6. For the next example, the question states, imagine a game in which on any play, which means on any turn, a player has a 20% chance of winning Taka 30 and an 80% chance of losing Taka 10. what is the expected gain or loss of the player in the long run? So we have the definition of a game where the player has a 20% chance of winning Taka 30 or an 80% chance of losing Taka 10. And we were asked to find the expected gain or loss of the player. For this problem, we can define a random variable x as the gain on a play. Let's express that information in a table. So we can have x and f of x. The possible values of x are 30 and negative 10. The probability of making a gain of Taka 30 is 0.2 or 20%, and the probability of making a loss of Taka 10 or a gain of negative Taka 10 is 0.8. So now we can find the expected value of the gain for the player. So the expected value of x would be simply equals to 30 times 0.2 plus negative 10 times 0.8, which equates to negative 2. What does this mean? What this signifies is, if the player continues to play this game over and over for many times, in the long run, it is expected that the player will make a loss of 2 Taka. Now for the third example. If the random variable x is defined as the top face of a tossed fair 6-sided die, what is the expected value of x? So x is defined as the top face of a fair die. So if we have a 6th-faced fair die and we toss it, x is defined as a random variable that identifies the value on the top face of the die. So what are the possible values of x? They are 1, 2, 3, 4, 5, and 6. And it was said that it's a fair 6-sided die. So the probability of the die landing on any one of these faces is equally likely. Or for a fair 6-sided die, the probability would be 1 over 6 for all of these values. In that case, what would be the expected value of x? Let's figure it out. The expected value of x would be equals to 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6 plus 4 times 1 over 6 plus 5 times 1 over 6 plus 6 times 1 over 6. If we calculate this, we get 3.5. So by the definition of expectation, we can say that the expected value or the mean value for the top face of a tossed fair 6-sided die would be 3.5. Now one might ask, a die does not have a decimal value. It cannot land on a 3.5. So how are we saying that the expected value would be 3.5? What this expectation signifies is that if we kept tossing a die over and over and over again many times and record the value that lands on the top face for all of those trials, the mean of all of those values would be approximately equals to 3.5. We will now look at a simulation of this particular example to hopefully make this concept even clearer to you all. Here is a simulator for the expected value of rolling a fair 6-sided die. The link to this simulator will be provided in the video description. We would recommend that you visit this site and try out the simulator by yourself. So we can see that the probability of each value of the 6-phase die is set to the same value, approximately equals to 1/6. That signifies that this experiment will simulate a fair 6-sided die. Let's roll the die once. If it's rolled once, the first value it lands on is 5. And since that is the only value we have right now, you can see that the average is at 5. Let's roll it again. In the second roll, we get a value 1. So after 2 rolls, the average value would be 5 plus 1, which is 6, divided by 2, which is 3. Similarly, if we roll the die again and get a 4, you can see that the average value increased by a small amount. If we roll the die again and again, and if we continue the simulation and we speed it up, you will see that over time, the average value of rolling this die is very close to the expected value, which is 3.5. So that is what we understand by an expected value. If we take a random experiment and we keep repeating it over and over and over many times, the expected value gives us the average value of the random variable over all those experiments. Hope that makes the concept of expectation clear to all of you.